Well, greetings, everyone. Happy Friday to you all. We're going to go ahead and give folks just another minute or so to come into the webinar and get settled. And we have an excellent presentation for you today. And so just give us another moment and we'll get started. While we are waiting, I do want to remind you that the IWCS 2025 conference is coming up rapidly. So we're in the very final stages of pulling together the program, and you'll probably have seen some registration opportunities to get some early bird discounts. So uh, keep an eye out on your email and also on our website to hear about the interesting and fantastic program that we have coming for you this October. Okay, well, why don't we go ahead and get started? I know that a few folks may be joining us in a little bit, but welcome to today's IWCS webinar series event. My name is Dave Cadu. I'm honored to be the CEO and director of IWCS, and I'll be your moderator for today's webinar event. A few housekeeping items before we get started. Please note, as an attendee, you're part of a wider audience, and as such, you'll be in listen-only mode. And also, this webinar is being recorded for posting on our YouTube channel and IWCS website. So you can feel free to share it with your colleagues or view it again as you wish. We encourage you to submit written questions for Grant, our presenter today, at any time during the presentation, and you'll be using the chat function to do that. So once you select or click on the chat on the right of your screen, you can type in your questions and be sure to hit the send button, and your questions will be addressed, time permitting, at the end of the presentation. So again, we thank you for being with us today. I guess good morning, good afternoon, good evening. I see from our registration that we've got folks from all over the globe. Some of you are late into the evening, so I hope you have a glass of wine or a beer. And again, we just thank you so much for being with us. Today, we welcome Grant Sheridan, a research scientist from Covestro. And Grant will be presenting his paper on fast curing next generation primary coating technologies, providing improved consistency in optical fiber performance and draw tower process. Dr. Sheridan is currently the research scientist of fiber optic materials at Covestro, developing the next generation of fiber optic primary coatings. Grant graduated from the Colorado School of Mines with a bachelor's degree in chemical engineering and went on to the University of Illinois in Urbana-Champaign, achieving a doctorate in material science and engineering. He is also focused primarily on small molecular diffusion through polymer networks. So again, we thank Grant for being with us, and take it away.
Awesome. Thank you, David, for the kind introduction and inviting me to this webinar and to close out the webinar series before the exciting IWCS coming up in Pittsburgh. I believe, is everything showing up okay, David?
Yes.
Awesome. Yeah, so today I'll be sort of presenting our work at Covestro on our next generation primary coating technology, as David said, to try and sort of meet the challenges coming towards the primary coatings in fiber optic manufacturing and providing a more improved draw tower consistency for these coatings and properties seen. So there are a couple of challenges that we see sort of facing these next generation primary coatings that we sort of need to meet or exceed. The first of which is sort of the switch from microwave to UV LED lamps. Now UV LED lamps are great. They provide simply more energy efficiency, lower operating costs, less hazardous, materials in them. So UV LED lamps are great for fiber optic production. Um, However, when we consider sort of the effect on primary coatings and primary coating curing, these UV LED lamps typically have narrower emission bands when compared to sort of these broadband microwave lamps used previously. Now, these narrower emission bands basically just limit the wavelengths available to sort of initiate the curing for the primary coatings and provide challenges there. In addition to the switch from UV LED lamps, um, we're also seeing, an increase in draw speeds for fiber manufacturing. Over the last decade, draw speeds have increased from 1,500 meters per minute to 2,500 meters per minute, and more recently are looking to exceed over 3,000 meters per minute. Now, this obviously improves the efficiency in fiber production. However, with respect to the primary coating, these ever increasing draw speeds just further decrease the exposure time available to cure and sort of lock in these mechanical properties to protect the glass itself. Now, these two are sort of a, 1-2 punch. Not only are we seeing shorter exposure times to cure the primary coating, but we also have a narrower emission band or less wavelengths available to photo initiate and cure the system itself. So these sort of operate as a 1-2 punch challenge that we sort of aim to address with our next generation technology. Thirdly, I put it as lower helium consumption, but this could also just be higher fiber temperature. With helium scarcity and costs, fiber production may look at lower helium cooling, lower helium consumption, which in turn would lead to higher fiber temperature. On the other side, if even keeping helium consumption and cooling constant as draw speeds are increased further, this would lead to more challenging cooling and higher fiber temperature in that aspect. So our work at Covestro is sort of aiming to develop these next generation primary coating and primary coating technology to sort of meet the switch to UV LED lamps, access draw speeds above 3,000 meters per minute, and be more insensitive to sort of fiber temperature for the mechanical properties. Now, to sort of demonstrate our next generation technology, we first ran our coatings and evaluated them using our in-house draw tower simulator, which is very handy for developing coatings as we were able to change the setup in-house. Our draw tower simulator is able to operate either on wet application or wet on dry application. So we could really tune the process to sort of the coating we're trying to develop. In particular, for this study or for this presentation, we are looking at a wet on wet application using UV LED lamps to mimic the switch in industry. For the draw tower simulator, we use metal wire and feed it running down, and then for the wet on wet, the primary secondary dyes is coated here, and then run through at up to 3 curing lamps or 3 UV LED lamps in this case. With our draw tower simulator, we're able to vary not only the speed, but obviously the number of lamps or lamp power to vary exposure time. So with our draw tower simulator, we're able to vary the draw speeds from 100 to 3,500 meters per minute and the number of lamps from 1 to 3 lamps. This allows us to sort of access an order of magnitude in exposure times from over 300 milliseconds all the way down to about 5 milliseconds for the shortest exposure time. Being able to vary the exposure time over this wide range really lets us evaluate these coatings and compare the next generation coating compared to our current coating technology in terms of cure speed and mechanical property buildup. So shown here is showing the cure speed of the next generation coating in blue compared to our current coating technology in orange versus exposure time. The RAU represents the reacted acrylate unsaturation, which is essentially just the double bond conversion measured via FTIR. So sort of the first thing that I would say pops off the page is just how much faster this next generation coating cures compared to our current coating technology. As we can see down here at the very short exposure time, this next generation coating has already achieved 80%, 82% cure at just 5 millisecond exposure time, while the current coating technology is sort of lagging all the way, down at 55% cure, which would pose challenges as draw speeds are increased, over 3,000 meters per minute, and exposure times are significantly reduced. Now, we did fit this data to a pseudo first order kinetic model to try and be more quantitative in our analysis between this next generation coating and the current coating. Shown here sort of as a benchmark, we looked at the time to 90% cure, 90% RAU, which we felt was a good number that was achieved on actual draw tower processes and manufacturing. So as we can see here, this new generation technology sort of decreased the time by about 1/3 from 30 milliseconds all the way down to 12 milliseconds. Furthermore, from the pseudo first order kinetic fit, we're able to extract a reaction rate constant. And we can see that this new next generation coating and technology improved this about 40%. So we feel that with the significant strides in the cure speed of this next generation coating relative to the current coating, we're able to meet these these faster draw speeds, an industry approaching 3,000 over 3,000 meters per minute. On the flip side, if draw speeds aren't really a concern, the significant improvement in cure speed could also possibly introduce operational cost savings. At the faster curing systems, you could imagine could lead to you having to use lower lamp power or fewer curing lamps to sort of achieve the same degree of cure as the current coating, which could possibly provide operation savings there as well. So in addition to the cure speed, we also feel that the mechanical property buildup is just as important, if not possibly more important, to ensure that we're protecting the glass itself. Because if you cure your system but you have no mechanical properties, then the primer coating isn't really doing a whole lot. So shown here, we have the normalized in situ modulus to sort of the maximum, the in situ modulus we see at the largest exposure time versus exposure time. And once again, we can see that the next generation coating is significantly faster at building up the modulus, building up the mechanical properties compared to the current coating technology. Once again, we fit this to a pseudo first order kinetic equation, and we can extract a rate constant for the modulus buildup in this case. Looking at the time to achieve sort of 85% the maximum in situ modulus, this next generation coating decreased this time by about an order of magnitude, from 78 milliseconds down to about 5-6 milliseconds, a significant improvement. Furthermore, there's even a larger improvement in sort of the rate constant of this modulus buildup. We see about a 2 order of magnitude increase in this rate constant, which sort of lends the fact that this next generation coating, the in situ modulus more or less plateaus very quickly after only a couple milliseconds in exposure time, lending to a more consistent in situ modulus with exposure time compared to the current technology. Now, if we combine the RAU and in situ modulus, this is sort of how we define our draw tower consistency. So we have in situ modulus on the y-axis and the degree of cure on the x-axis to define draw tower consistency. So if we look at the current coating first in orange, we can sort of see that it sharply increases as we approach full degree of cure, 100% cure, indicating just how sensitive it is to any small degree of variation in the cure. So you can imagine any process variations, unintended process variations that very slightly affect the cure of the primary coating will lead to drastic changes in the modulus seen. Additionally, we would anticipate that upon subsequent curing, during cabling or other curing processes, the modulus of this current coating would jump more drastically due to this steep increase in sensitivity shown here. Now, if we look at the next generation coating in blue, we could see that unlike the current coating, the next generation coating has plateau with increasing RAU, leading to it being less sensitive to variation in degree of cure. We believe that this significantly improved draw tower consistency, as any small variations in processing or in cure will lead to significantly smaller variations in the in situ modulus seen here. Additionally, we would anticipate that with subsequent curing steps, we would see a smaller jump in the in situ modulus as well. We sort of lend this improved draw tower consistency and plateauing to its significantly faster in situ modulus buildup in this next generation coating. We building up the polymer network, the mechanical structure early on in the curing, and with additional curing doesn't contribute as much, leading to the plateau. I believe my colleague would be presenting on this more in October in Pittsburgh, so you're welcome to, we could connect in Pittsburgh as well. Now you might be saying this is cool, but it's on a draw tower simulator. We use a metal wire. We don't have to worry about fiber temperature. So we took this next generation coating to the Nextrom R&D Center and trialed it on an actual draw tower. Shown here are our process sort of limits. We varied the draw speed from 1300 to 2800 meters per minute, as well as had varying glass temperatures from 42 to 120 degrees Celsius. Now, previous IWCS papers had noted that coating geometry, coating thickness is a very large concern with fast draw speeds and high fiber temperatures, as sort of controlling thickness over a range of process conditions would be very important for consistent fiber production. So one of the first properties we sort of looked at was the primary coating thickness, shown here, over the range of fiber temperature, 80-degree range of fiber temperature. As we can see, there's about a 5-micron decrease over the entire range from 40 to 120 degrees Celsius, with about 1.2 micron standard deviation in primary coating thickness. We believe this demonstrates the sort of robustness of this next generation primary technology, lending to only a 1.2 standard deviation or a 5-micron decrease over a wide range of fiber temperatures all the way up to 120 degrees Celsius. We believe that the fast curing nature, the fast modulus buildup of this next generation coating lends itself to the robust coating thickness, as we're able to sort of lock in the coating geometry very fast before the fiber temperature sort of is able to thin the coating more and more and lead to these inconsistencies in coating geometry. Next, I'm showing the degree of cure of these coating versus the relative UV dose, and have split it to show sort of the glass fiber temperatures below 100 degrees C in blue and those above 100 degrees C in red. So as we can see, this next generation coating cures extremely fast as well, on an actual draw tower. To sort of meet the high draw speed processing demands in industry. We were able to achieve, 90% degree of cure even at only 20% of the relative UV dose, of the maximum UV dose. Further demonstrating this extremely fast curing. Additionally, due to the extremely fast curing, the REU remains relatively constant over all relative UV doses and glass temperatures, reaching 90% almost right away. It'd be very stable in terms of processing conditions if there are any variations, because there's not a lot left to cure at that point. So we believe that this extremely fast cure speed will lend well to the the ever increasing draw tower speeds. Now, we looked at REU, so we have to look at the in situ modulus and normalize in situ modulus buildup versus the relative UV dose, shown here again for fiber temperatures below 100 degrees C and those above 100 degrees C, where if we look at the blue data, the glass temperatures below 100 degrees C, we can see that we reached about 80% of the in situ modulus at only 20% UV dose again. So once again, very fast curing, very fast modulus buildup to protect the glass and develop the mechanical properties. Additionally, we could see the improved consistency, as there's only about a 10% standard deviation in the normalized in situ modulus over all relative UV doses. Now, when we look at the high glass temperatures above 100 degrees C, we do see a small 10-20% jump in the in situ modulus relative to those below 100 degrees C. However, we believe conventional coatings typically show a 2-3-fold increase with increasing temperature. So these next generation coatings further show more temperature stability and more insensitivity to sort of the glass fiber temperature, in addition to the coating thickness shown before. Just like we did with the DTS data, we're looking at the draw tower consistency on this, actual draw tower at the Nextrom R&D Center. So we have the normalized in situ modulus versus the RAU. As we can see, once again, we see very excellent draw tower consistency over all the processing conditions, all the draw speeds, all the fiber temperatures, where the in situ modulus quickly plateaus and is exhibiting, more insensitivity to the REU as our current technology had shown on the DTS. This sort of enables maintaining an in situ modulus level, even with small drifts in process conditions, and should reduce the modulus jump with subsequent curing. Now, cure speed, modulus buildup coating thickness is nice, but we also wanted to test actual fiber performance, and one of the first ones we looked at was low temperature microbending performance to ensure, it will still operate as a fiber optic cable. So using the method D, basket weave method, to sort of look at low temperature microbending performance, where we use 2.5 kilometers of fiber, wrapped via basket weave at wind speeds of 100 meters per minute. We followed this temperature profiling. So we took the fiber down to negative 40 degrees C and negative 60 degrees C as our low temperature performance measurements. As you can see here, I have the microbending performance for this next generation coating at both negative 40 and negative 60 degrees C, and the change of attenuation associated with them. Sort of as a sanity check, we can see that the change in attenuation does increase with increasing wavelength, which is an understood and expected phenomena, as the longer wavelength is more susceptible to microbends and signal loss. So as we can see, this next generation coating provides very good low temperature microbending performance at negative 40 degrees C. We're about an order of magnitude below sort of a threshold of 0.05 change in attenuation. So at negative 40, we were at 0.005 dBs per kilometer. Now, when we do go to negative 60, we do see an order of magnitude increase relative to the negative 40 degrees data. However, this data is still well below the 0.05 sort of threshold, with an average of about 0.25 at the longest wavelength, 1625 nanometers and negative 60 degrees Celsius, providing great low temperature microbending performance. Now, the increase from negative 40 to negative 60 degrees C is well understood as the primary coating, approaches its glass transition temperature and sort of undergoes a transition from a rubbery network to a more glassy network, increasing sort of the microbending there. But overall, very good low temperature microbending performance seen all the way down to negative 60 degrees C. In addition to the low temperature microbending performance, we also looked at the fiber strength. Previous IWCS publications had demonstrated or raised the concern of the effect of high draw speeds on fiber strength. So shown here is just a quick overview of our fiber strength testing conducted with sort of two capstans. So we have a 6 and 20 centimeter diameter capstan. And shown here are the cumulative failure probability of five fibers of the next generation coating, sort of encapsulating the extremes of the conditions run, including draw speeds from 1300 to 2800 meters per minute and glass temperatures from 42 to 120 degrees C. Despite the extreme range in draw speed and glass temperature, all 5 fibers demonstrated excellent fiber strength over 5.1 gigapascals, with M values close to or over 100, which indicated excellent data point consistency. So overall, it's been hopefully demonstrated that this next generation primary coding and primary coding technology improvements over the current technology. It demonstrates extreme cure speed improvements over the current technology, modulus buildup improvements, and draw tower consistency improvements to sort of meet the switch to UVLED lamps, as well as draw speeds in excess of 3,000 meters per minute. We also enable better low temperature microbending performance, in addition to the significant improvements in cure speed. And these next generation coatings also provide robust draw process capability, being able to meet the high draw speeds, higher fiber temperature on UV LED curable, while maintaining consistency with coating geometry, in situ modulus, and RAU. Now, this was just one of sort of the coatings from this next generation coating technology. And based on this technology platform, we were able to adjust and fine-tune the coating and fiber performances for different applications with excellent flexibility. So we'd be open, you could talk to us in October at IWCS, or reach out about any interest you might have, or yeah. So I don't know if there's any questions as well.
Excellent. Again, Grant, thank you very much. Great new technologies, and obviously very important to the future of our optical fiber transmission technologies and network infrastructure. So thank you for that. Again, any of you have any questions for Grant, please enter them in the chat, and we'll ask them. I do have a few questions here, Grant, to get started here. How does the microbending compare to the current coating technologies that are commercially available?
Yeah, so for our uh, for our current coating technology, we have been able to further push sort of the low temperature microbending performance, push uh, better better uh, better performing, change in attenuation, especially at -60 degrees C, where we really challenge the glass transition temperatures of these primary coatings. So we've been able to further advance and further decrease the change in attenuation at the very low -60 degree limit.
Good. All right. How do these new coatings provide for, sufficient pull-out force?
Yeah, so of course, the adhesion to the glass is very important, and pull out, strip force are also very important properties. We're able to sort of tune the adhesion, or the pull out force for the certain applications. Um, with this one in particular, being sort of the start of the technology, we were able to achieve around 3 to 5 newtons of pullout force. But through further development, we were able to sort of push that up higher to 8 to 10 newtons. But obviously, too high adhesion is also not desirable. So we've been able to develop a wide range of adequate pull-out force above 3, 4 newtons.
It's great. Very good. What UV LED lamps were used during your tests, both on the simulator and the Nextrom setup?
Yeah, so we're using a cool UV technology. Um, if you want to reach out, we could provide more information on that. But we're using the cool UV technology, um, UV LED lamps, if that answers
Okay.
your question.
Yeah, and I will be providing Grant's email address for you if you want to reach out to Grant directly. You may not be able to answer this question, but I'll ask it, and maybe you can just give a range. But
Mhm.
the question was, what's the approximate cost increase of the new coatings versus conventional coatings? Um, how do you see that? And you don't have to answer that question, but
Yeah, so obviously I'm not on the business side of things. So I don't, I'm not aware of, what sort of costs we're looking at, but we are more than welcome to work with you on sort of costing and things like that. But
yeah,
we're well aware of, cost constraints with fiber
yeah.
manufacturing these days.
Yeah, and for those kinds of questions, it'd be great if you were with us in Pittsburgh. I know
Yeah.
Covestro will be there in full force. And just the good news is, while we're in Pittsburgh, Covestro has their North American corporate headquarters there in Pittsburgh. So I'm sure you can find answers to those kinds of questions. Um,
Yeah, or
is
like,
is is the
oh,
new coating susceptible to cavitation damage in the primary during processing at high tension?
Yeah, so we've been seeing sort of improved cavitation resistance with some of this with these new coating technology. Now, every draw tower process condition is different, so we'd be happy, to sort of evaluate that with you. But with the DTS and at least with our metrics, we do see sort of improved cavitation resistance.
Okay. Um, what range of properties are we able to obtain with this technology?
Yeah, so since sort of the development or through the development of this technology this was sort of the first uh, application development we did for single mode, but we're sort of trying to expand it from, single mode, but also some multi-mode applications as well. So we're trying to sort of encompass most applications with this new technology.
Good. Um, I think unless there are any more questions from the audience, we have one more question, Grant. Um, how will this coding going to be impacting on making the end product? So I guess it's a processing question, what differences are. Um, for example, if we make ribbons of these using these coatings, do you have any simulations or trial results on the cabling, and how do fiber losses um, from the fiber stage to the jacket stage?
So I understand the question
Yeah.
due to this being a primary coating, you would have a secondary coating on top of it that would be, so it shouldn't, it wouldn't anticipate it affecting sort of the ribboning, and all that. But I think on the second half of the question, in terms of cabling, or I guess, yeah, curing and ribboning,
And
we
losses,
we
yeah.
wouldn't we would anticipate, a smaller in situ modulus jump relative to our current technology. So we would anticipate smaller loss there, as the in situ modulus doesn't jump up as much. But we're still developing this technology, and would be happy, to work and evaluate that with you as well.
Good. And what was the final coating diameter for the microbending test? Will the new coating still perform well in terms of microbending loss if the coating diameter is reduced, for example, to 200 micron or 160 micron?
Yeah, so this is 250, um, and that's sort of the new, I guess, the new aspect of the new branch. We're sort of branching out to multi-mode or thinner coating levels, and we would anticipate, a similar microbending performance at that level, due to sort of uh, being able to push the TG of the glass transition of these lower. So, but we're sort of, yeah, exploring that and expanding to that uh, thinner, I guess, fiber at the moment. So we would once again, if you want to talk to us in October or reach out, and we could sort of explore that with you as well. But this was, yeah, all done at 250. So for sure, there's more work
Great.
there.
Yeah, and again, as Grant mentioned, we look forward to seeing you all in Pittsburgh, and Covestro is once again contributing greatly to our technical program and the continuing story over many years. And it's just the evolution of this great technology. So, Grant, thank you so much for bringing this to us again. It was outstanding back last year's conference, and we look forward to the continuing story this year in Pittsburgh. So I want you all to make note of Grant's contact points being shown here. Should you wish to contact him after today's event. And also, each of these IWCS webinar series events are recorded and are archived on our YouTube channel, and you can easily find them from our IWCS.org website. So you can go on and you can look at all the history. We have over 100 great presentations archived there that are still valid today for your viewing. Typically, we conduct our technical paper presentation webinars every month on the third Friday of each month. But as we're getting close to the conference here in October, we're going to forego that in September and October. And so our next technical presentation webinar event will be on Friday, November 14th at 10:30 a.m. Eastern USA time. You will be getting notifications for these events, so feel free to share those with your colleagues so they can join in as well. And we'll be making an announcement as to the topic. It will be a well-received paper from our 2025 event in Pittsburgh. So look forward to having you with us again in November. I do want to recognize and make sure that we all appreciate the support, both from technology and contributions, but also they contribute financially to the success of our Cable and Connectivity Industry Forum. Our partner level sponsors provide such strong leadership and generosity, and we would not be able to bring these important technical innovations to you and our global community without their strong support. So again, we thank you to all of these leading suppliers in our industry. Again, I want to remind you that our 2025 Cable and Connectivity Industry Forum is taking place in Pittsburgh, Pennsylvania, a great location. The city has really revitalized itself with fabulous restaurants and entertainment. There's quite a few sporting events going on. There's a football game and hockey game going on that week. So we hope you can join us the last week in October. And our friends at Covestro a lot will be local from their corporate headquarters, so feel free to reach out to them. For again, for so many years we've had such incredible interaction and networking opportunities with your colleagues from all over the world. And also, I wanted to make mention at this year's conference, we generated some really fabulous special sessions. These are in conjunction with the technical sessions that you're familiar with the technical papers, but these are very topical, trending information from a variety of standpoints. So again, these special sessions on AI and machine learning for network infrastructure, sustainable solutions for both powering and data cables, and then powering the grid of the future, smart connectivity, the resilience, the innovation, and all of the energy transitions that we need to do to provide for expanded data centers and AI and the future of quantum computing and all of that. So you'll want to be part of this and hear what's trending and what's going to drive our technology for the future. And again, for over 73 years now, IWCS has been the recognized leader for showcasing the new technologies in our cable and connectivity industry, both products, processing, and applications. So our 74th anniversary conference will be in Pittsburgh at the end of October. So please watch your inbox, your social media, and of course our website to learn more as the exciting information becomes available. Registration is now open with some advanced discounts, and our preliminary program is available on the website for your view and is constantly being updated and finalized. So again, we want to thank you all for participating today, and we hope to see you in Pittsburgh. And you all have a great weekend and enjoy the rest of your summer. I can't believe how fast it's passing by. So enjoy the rest of it. Anyway, thank you. Take care.